Okay, so we'll get into now the idea of using bolts in static loading applications. And also tied to this, I'm going to put in the idea that bolts are intended to be preloaded, and how do you know how much to preload them, first of all, and then how do you know how to get that preload? If you know how much preload you are going for in a bolt, there's a couple of different ways that you can actually achieve that in practice, or at least get close to achieving that in practice. And so we're going to talk through these things in this example problem. So basic idea here is I'm showing a multiple bolt connection here just to kind of give you an example of something like that. For now, I'm going to make this bolted connection pretty simple to where the axial load that is being applied based on the geometry of how the bolts are put in there, it basically will evenly distribute that load between the 4 different fasteners. We'll see another example where that doesn't happen. We'll see that next time. But for now, we'll just say, if you have something real simple like this, additional load can be assumed to be distributed evenly between the fasteners. Okay, and I've actually specified that we're going to have steel fasteners. M10 by 1.5 is the size of the bolt as far as the kind of the thread size and the thread pitch. It says we're using a property class 9.8. We'll get into what that means here in just a second. It's going through 2 steel plates, each 12 millimeters thick. On the other end, we're going to put thick nuts with no washers. Okay, and we have to be able to carry 20 kilonewtons of axial force on this bolted connection. Question came up just a second ago, what does this squiggly line mean? I was just trying to represent that it's like we've welded pipe onto little flanges there, and so that just represents a weld. We're not working on the weld right now, we're just thinking about what happens in the bolts. So it's just an artistic thing for what it's worth. All right, so this is where we're going. What we are trying to find, we need to find an appropriate pretension if we would like to be able to reuse these bolts. So let me actually camp there for just a second. There are a couple of different ways that we can use bolts like this. One of the ways is that we can specify that enough load has been put in the bolt that it's very possible that we will start to cause plastic deformation in the bolt. Okay? If you want to be able to reuse bolts, then you probably don't want to specify plastic deformation in the bolts. Okay? So there's a guideline in here about how much pretension is probably appropriate if we want to be able to reuse the bolts versus there's another technique where you don't expect that you're going to be able to reuse the bolts, and that every time you would say disassemble or reassemble an assembly with these bolts, you would replace them. Okay, so we are planning on reusing the bolts. Let me actually say one other thing about that real quick. If you will flip to, I believe it is on page 433, it gives a typical stress-strain diagram for bolt materials. And you will notice that that stress-strain diagram increases all the way up to where it fails, where it actually fractures. S sub UT would be where it fractures. The reason for this is that these bolt materials are typically not sort of virgin steel, right? They are usually some sort of cold working process or other types of processes are generally applied to high strength bolts so that it makes them to where they do not have as much plastic deformation that they can go through before they break. Okay? It does have some plastic deformation it can go through because, and you can see that by the little curved piece at the end, but not as much as some of the steels that we have looked at back in the past, more ductile steels. And so this is an interesting, setup of these bolts that, this is why they can tend to sort of exhibit more of a brittle type of behavior rather than a ductile type of behavior, although they are not fully brittle because they do have some ductility to them up there. All right, so just figured I'd mention the stress-strain curve and how it looks for typical bolt materials. All right, the next thing here we're supposed to find is an expected elongation for the amount of pretension that we would like to specify for this bolted connection. Part C, we're actually going to do this kind of the same task two different ways. So the task of part C is basically, how would you tell someone who was going to install these bolts, how would you tell them how to achieve the pretension that you wanted to specify? And there's two different techniques that are listed here. One of them is essentially using a measurement technique of torque on the bolt while it is being installed. I'll just go ahead and mention about that. This is not the most reliable way to get the amount of pretension that you want. It's a little bit more reliable to do the second technique that is shown here, and that is once you get the nut snug on a connection like this, you can specify how many more turns you would want to apply to the nut in order to stretch it a certain amount. So this is called the turn of the nut method. Basically says, you know, you get it snug and then you keep track how much further you turn the nut to get the kind of pretension you want. There's a third technique that's not actually mentioned here, and it is basically direct measurement of how much elongation you would have on one of the bolts. What that would look like is using some sort of a caliper or a micrometer to basically, you know, measure directly across from the end of the bolt up to the head of the bolt. And you could directly measure how much deformation you caused, how much elongation you caused of the bolt, and therefore you would be able to know how much pretension you caused in the joint. Okay, that is the most reliable way to do it. The downside of that method is that it's essentially impossible to do it if you have what's called a blind hole. A blind hole is one where you don't have access to the hole in which you've installed the bolt, and so you can't get a tool on the back side to be able to do a direct elongation measurement. Those of you who are auto mechanic types, what have you probably done to try to get certain pretension in bolts? What's kind of typical? Yeah, a torque wrench, right? Some of you have used a torque wrench. That is an instrument that is used to measure the amount of torque that you put on a fastener as you are putting it in place. And so that's a very common way to do it in the context of auto mechanicking. You know, it is actually not, it's better than just, you know, going blind and just putting a certain amount of torque on there that feels right or whatever. It's better than that, but it's still not a great way to know exactly how much pretension you have applied in a bolt. Part D, we're going to figure out the factor of safety against exceeding the proof strength of the bolts. Okay. Now, the reason we actually have more than one way of specifying sort of a factor of safety, or in another case it's called a load factor, we have more than one way to specify what constitutes a failure for a bolted joint. And the reason for this is that it's actually, you know, a lot of times what we want to do with a factor of safety is we want to be able to know how many more times the amount of load can we put on it before we have a failure. Well, due to the fact that we are pre-tensioning these bolts and some of the added load goes into relaxing the member that it's clamping rather than going into just increasing the load in the bolt, it actually makes that sort of a nonlinear relationship. You can't just multiply by, let's say, a factor of safety that you compute to figure out how many more times load you can apply to it. And so we have more than one technique of specifying kind of how bad is our loading situation on our bolts. One is factor of safety against exceeding proof strength. Another one is a load factor. And then the last one is basically a whole other idea of at some point you've put so much load in the bolt that you have the capacity to actually cause there to be separation between the pieces of material that you are clamping. You actually can stretch the bolt enough to where you don't have any more compressive stress built up in the pieces that you are clamping, and that generally constitutes a failure as well. One of the reasons that constitutes a failure is that once that happens, then all of additional load you put on after that goes into an increase in stress in the bolts. There is no sharing of how that load gets distributed, and that can mess with your calculations. That's one problem with it. And then the other problem that sometimes comes up is that if you have separation between parts like this, one of the ways that bolts are used a lot of times is like to hold pressure, hold internal pressure, like a fluid pressure or something inside of the connection that's being made. And you can see why having joint separation would not be a good thing if that's one of the things you're trying to do with a joint. Okay, so there's any one of these can constitute a failure, and so we are going to look at all of them. All right, so shall we get started? Yes, we shall. Part A, an appropriate pretension if we would like to be able to reuse the bolts. Okay, so what we need to do for that is first have some sort of a guideline for, sort of even how we would get started with this. And so I want to turn your attention to equation, there's a little bit of discussion beforehand, but equation 831 gives you an idea of how you can approach sort of a target preload that you might want in your bolts. So equation 831. And right there it basically has a, kind of two cases. One is, do you want to be able to reuse your fasteners or don't you? Okay? And the guideline that is represented by equation 831 is that if you do want to be able to reuse your fasteners, a good target preload is 75% of your proof load. Okay? Proof load, if you go back to the stress strain curve that I showed you a few seconds ago, the proof stress in a bolt is actually a little bit less than the yielding strength of a bolt. The reason for this is that when you define a yielding strength on a stress strain curve, it is basically a point where you have a detectable amount of plastic deformation. The problem is, in materials, you actually get plastic deformation before you can detect it. Okay? And so what they do with a proof strength is they actually derate the yielding strength a little bit and say, we pretty much want to try to make sure that we're not getting plastic deformation in any part of the material. All right, so these proof strength values are values that are listed in a couple of tables in here for various properties of bolts, property classes of bolts. Okay, so that's kind of why the proof strength matters. But what we're going to take from this is that if we want to use our fasteners again, we are going to set our preload to be 75% of the proof strength. Or exactly, actually, since it's F sub P, this is not proof strength, this is proof load. We get proof load by using a proof strength of the material and an area. Okay? So this is kind of our starting point. So how do we get proof load? Because what we're trying to do is figure out F sub I right here. How do I get F sub P? Well, F sub P, all right, using just our basic stress equation, stress is equal to force over area. That means your proof force is equal to whatever your proof strength is times what? Okay, the area, and actually I'm going to put a subscript on here of A sub T, because that is, in the tables, they actually call this the tensile stress area. This is kind of a derated area that takes into account the idea that you have threads cut on the member, and you've reduced the area of the member by having some of the material removed in the threads. Okay? All right, so where do we get these things? Well, first of all, let's look at A sub T. Okay? A sub T for a, what do we have? We had a M10 by 1.5 property class. Okay? We have to flip over to where the geometry of various kinds of bolts is listed. That would be on table 8.1 for metric. Okay, so table 8.1. It says here that for an M10, okay, that is the nominal major diameter, so it means we have a 10 millimeter nominal major diameter of our bolt. That's in the left column. Then we actually have to look and make sure we're in the right pitch series. Okay, that's what the second number represents there for an M10 by 1.5. You'll notice that in the left column you have 1.5 pitch. So this actually gives me a chance to mention that how you specify a number of threads per unit of length is different in the metric system than it is in the US system. So what we've done so far with our previous problems is we have done a measurement that is in threads per inch, right? In other words, a number of threads per unit of length. In the metric system, what they use is they say, how big is each thread? All right? And so that's what this number is. It means that each thread is 1.5 millimeters in length. So it's essentially the reciprocal of what you do in the US system. Okay? Because we got to make everything weird. We got to make everything hard, right? So I want to mention that, though, is that that is reversed in the metric system versus the US system. And we have a 1.5, which means that we're in the coarse pitch series. If it had been by 1.25, then we would have been in the fine thread series. So we're over on the left set of data in table 8.1, and we need to find the tensile stress area. It says there that it will be 58 millimeters squared. Okay? All right, so we have that, but how do we know what the proof strength is? Okay? For that, we need to use this other piece of information that was given up here, that we have a property class 9.8. That is referring to the strength of that bolt. Okay? And there's another table, not in that table, there's another table where it gives us some guidelines for various strength classes of bolts. And so if you go to table 8.11, all right, 8.11, remember we've got a 9.8. We look at this entry in here, and I'll just mention here that it also gives you ranges of diameters that you can expect for each of these classes. That's the first thing that it says. We are in that range, so that's comforting. It says that our proof strength is 650 MPa. Why do you think it says minimum proof strength? Yeah, it's kind of to be conservative. One way of thinking about this is that always material properties like this, strength properties, they're basically always, they occur as a statistical distribution, not as a deterministic value, right? And so when you're designing stuff, you typically want to make sure that even if you've got the weakest one of the batch, you're still okay, right? And that we kind of almost ignore the fact that a lot of them might end up being stronger than this. We just basically say we want to make sure we're safe even if we got the worst one, all right? So that's why we have the word minimum in the heading of that table. All right, so now we go over here and we say that our initial loading, our preload, which they denote this as F sub I, is going to be equal to 650 MPa times 58 millimeters squared, okay, times 0.75. All right, and what that gives us here is 28.28 kilonewtons. All right, and this is per bolt, right? This is, you don't distribute this one. You don't say that that's, divide that by 4 or anything. Each bolt is loaded to this amount of force for the preload side of the question. All right, so we're done with part A, finally. Next, let's actually look at part B, an expected elongation for this pretension. What is it that we need in order to get that? What relates force to deformation? Hooke's law, right? So we need, well, maybe we'll say the force in the bolt is equal to spring constant of the bolt times the deformation. Elongation would be another word we could use for deformation, right, of the bolt. All right, so that means we need K sub B. So what does that mean? Before I can find K sub B, I need to know some other things, right? Page 418, table 8.7, remember that process we went through last time? Okay, we need to know how much threaded length and unthreaded length we have in the grip. We need to know the cross-sectional areas of each as well. So I'll try to be fairly quick about going through this process. So first of all, what's the grip? Tried to use as kind of a little bit more simple to kind of make it a little quicker. The grip is how far? 24 millimeters. Okay, that was kind of step one. Step two is we need to know the minimum length that we need for our fastener. Okay, to get that, I need 24 millimeters plus what? The height of the nut, right? We don't have to worry about the washer this time because I said we're not using a washer. We need to know the height of the nut. So we go flip back. That's in table A31. And we have an M10, and it said we're using a thick nut. So we're going to go across to where we find the thick nut. It says it's 9.3 millimeters tall. Okay, and again, that's on table A31. So my minimum length that I need is going to be equal to what? 33.3 millimeters. Okay, so now what I need to do is flip to another table where I pick out something that's not weird, right? Because if you call up and ask for a 33.3 millimeter bolt, you know, again, the answer will either be laughter or the answer will be, okay, we can make that for you. How deep are your pockets? Okay. So what we're going to do here is we're under the millimeters in table A17. And it says there the entries go 30, 32, 35. All right. Remember, this is kind of a stand-in for if you actually have a bolt catalog you're ordering out of, you would want to order a bolt that really exists. All right, something that they already make generally. All right. This, you know, doing this little step is kind of a stand-in for a step like that, trying to do something that's common. So we end up with 35 millimeters is what we would expect here. This is table A17. Okay, so we're picking a 35 millimeter long bolt. The next step that we're going to do is figure out how much of that bolt has threads on it. Okay, and the guideline for that is you take 2 times the diameter. They call this L sub T like this. You take 2 times the diameter. Okay, yeah, we've got to be in the metric series now, where the length is, okay, the length is 35 millimeters. That puts us in our shortest sort of series of this, and it ends up giving us 2D plus 6 millimeters. Okay, so that would be 26 millimeters. Okay, this is again in table 8.7. There's a procedure we're going through to figure out each step. So this step that we just did here is how much of the fastener is threaded. Okay, it's not numbered, but all this whole procedure comes out of table 8.7. Okay. So now we have 26 millimeters here, and then what? Okay, the next thing it says is we want to know the length of the unthreaded portion in the grip. And the way we get that, they label it L sub D. The way we get that is we take the overall length of 35 millimeters, and we subtract off the amount of length of the threads. That makes sense, right? Okay. And so what that ends up giving us is 9 millimeters. Okay, the next thing we do is we figure out what is the length of the threaded portion in the grip. This isn't the total amount of threads, this is just how much of the threaded portion lies within the grip. And so here you take your grip length, 24 millimeters, and you subtract what you just found for your unthreaded length. Okay, and when we do that, we end up with 15 millimeters. Okay, moving on from there, we now need to know what are the areas. Okay, so I need to know what is the area of the shank portion. For that, you just use a plain old area calculation, pi times 10 millimeters. Okay, squared over 4. All right. And that just gives me 78.54 square millimeters. How do I get A sub t? Right, already got that whenever I looked it up. Okay, so A sub t is just going to be equal to 58 square millimeters. That's the tensile stress area that we have for those fasteners. All right, now we have all the parameters that we know to be able to compute K sub B. All right, and this is basically the area of the unthreaded portion, 78.54. This is at the bottom of table 8.7. 78.54 square millimeters. Times 58 millimeters squared times the elastic modulus of these bolts, which again we just assume they are steel. Whoop. And we're in a metric system here, so what should I put in for my E value? 207 gigapascals is what that comes out of table A5 at the back of the book. And we divide this by the area of the unthreaded portion, which is 78.54 square millimeters, times the length of the threaded portion. Okay, keep in mind, you know, you have the area of the unthreaded times the length of the threaded, and you're adding to that the area of the threaded times the length of the unthreaded. All right, and once we put all those things in there, this ends up giving us 554.6 The units on this are meganewtons per meter. Okay, but that actually, I mean, it's a nice thing for us to know. That's not ultimately what we were trying to find in Part B. What are we trying to find in Part B? Yeah, how much elongation should we see in the bolt to get the kind of preload that we want? Okay, so to get that, we basically say delta, and we can even put on here delta sub I. That's not an uncommon notation we could use. This means kind of our pre-elongation is going to be equal to the force that we need in the bolt. We had that a few seconds ago, right? F sub I. Okay, let me just put it in here. F sub I over K sub B, and then we'll put it in. F sub I was 28.28 kilonewtons. This will be divided by 554.6 meganewtons per meter. Okay, and you would want to make sure you dealt with all of these units as you punch these things in. But if you do that then you should end up with an elongation prediction here of 0.051 millimeters. All right, so you generate 28.28 kilonewtons of force in the bolt if you elongate it by 0.051 millimeters. Questions yet? All right, so we have now done part B. Let's do part C. Part C says we need to recommend a bolt torque so that we can get this kind of pretension. And let's just say that anywhere we have contact between parts, let's say that we have a friction factor of 0.2. Okay, which may be achievable if you use some sort of an anti-seize compound or something like that. It's a pretty low value, truthfully, but it's, you can get these values. Good chance for me to mention that is that using some sort of an anti-seize compound is generally helpful. One of the reasons for that is that during installation of a bolt, you are not only putting in the preload, you are also twisting it at the same time. And if you go back and think about what that would mean with the context of failure theories from Chapter 5, what that means is that during installation, you are increasing the amount of stress that you put in it relative to what you would predict with just a pure tensioning. Now the thing is this is kind of good and bad. One of the good things about that is that it makes you more prone to break your fastener while you are installing it, because you're putting extra stress in there that you hadn't necessarily accounted for. But that's actually not really a bad thing, because if the fastener's going to break, it'd be good to break it while you're installing it rather than having it break in service. Would you agree with that? If it's going to break, it's probably better to break it beforehand rather than later. What tends to happen with the bolts is that, yes, you do put that twist in them when you install them. It actually, due to friction, it will a lot of times maintain some of that twist that you put in the bolt while you were putting the torque on it to be able to install it. But over time, the friction that holds that torque in place does tend to relax. All right? And that actually tends to take you back down to the stress levels that you would have predicted just with a pure axial force rather than axial plus torsional. All right? So after a while of the bolt being in place, it will have reduced back down to just having that axial force in it. And so that basically means you're not using up that available sort of extra stress that you could have in the bolt with that twist action, and now it's available to carry even more applied load if that's something that you end up doing on the fastener. So anyway, figured I'd talk through some of that, but it is kind of a good thing, actually, that if a bolt is going to break, it will usually break during installation, not during service, unless you do some sort of strange overloading of the bolt. Okay, so we need to do a recommended bolt torque. So there's actually a really handy equation that we have in the book. The equation, I'm going to go over here to section, let's see, 8.8. It talks through the idea of bolt torquing. It goes back and it uses equations that are very much similar to the kinds of equations we did while we were doing power screws. So kind of the same thing we're trying to do there. We're basically trying to figure out, kind of how much of the torque goes into friction and how much of it goes into actually creating axial force, right? That's generally what those equations did back when we were looking at power screws. So we're using those equations here again. I'm actually looking here at equation that's labeled C on page 430. Okay, it gives us a kind of a one-size-fits-all equation to figure out bolt torque, right? And what it says is that we're going to take here and do the mean diameter for a, I'll just write this whole thing up here. D sub m over 2d is the first term. The next term is tangent of lambda plus f times the secant of alpha over 1 minus f tangent of lambda secant alpha. Okay, and then to this I'm going to add 0.625. Times f sub c. This is so you can have two different friction factors, one for the head of the bolt and one for the threads of the bolt. In our case, I just gave you one factor. We're going to use it for both of those, but this gives you a chance to use different values for each of those. You multiply this now by the preload, f sub I, times the nominal diameter of the fastener. All right, so probably most of this makes sense. The two things that I will point out here is that for threaded fasteners, what do we use for dm? dp, and what's dp? Okay, you calculate dp based on that footnote that was in table, it's actually both in table 8.1 and 8.2. All right, and it says that you calculate this with d minus 0.649519 times the pitch. Okay, and so what we're going to do here is put in D was 10 millimeters minus, again, 0.649519 times, what's the pitch for this nut? Okay, you can just directly use the 1.5 millimeters because it's a single thread, which you can assume unless it gives you otherwise. So you have a single thread, 1.5 millimeter pitch. Okay, so this gives us 9.026 millimeters. That's what we use for D sub m in this equation. What we use for regular D is just 10 millimeters, so that's not weird. We've already talked about F. What do you think we use for alpha? Okay. Remember, alpha for the equation that we had for power screws was basically a statement of the angle of the thread itself, that the thread has a certain profile to it. For Acme threads, 2 times alpha was equal to 29 degrees because that would basically was specified from one thread to another thread, whereas alpha here is specified relative to a line that's perpendicular to the axis of the fastener or of the thread, whatever it would be. All right, so what we need to do here is figure out what this value is for a threaded fastener. That can be found on page 403, where it shows you what the profile looks like, the thread profile looks like for general threaded fasteners. And here it says that you have a total angle from one thread to another of 60 degrees. Okay, so what's alpha? 30 degrees. And so if you want to check that out, that's on figure 8.2. Okay, so that's alpha. Now we have this other thing of what is lambda. Okay, well, rather than tell you what lambda is, why don't I put in here and say tangent lambda is equal to L over pi dm. Okay, I don't know why they actually put it in here this way, but to give you the idea of what this lambda is, it's sort of the angle of the thread pitch, or as the thread goes around. Let's say it's like you were climbing This would be the angle that you would feel if you were climbing up a thread that was built this way. Anyway, I don't prefer looking at it that way. I prefer looking at it as tangent of lambda, this whole thing, is equal to the lead of your screw over pi dm. All right, well, how do I calculate this? I put in my lead. What's my lead? It's a single thread, so my lead is equal to my pitch. Down here I've got pi times that mean diameter that I just had. I think there's some discussion on it. I don't remember where it is off the top of my head. But basically the idea there is that when you have one thread, lead is equal to pitch. If you have two threads, lead is equal to 2 times pitch. All right, so it's an argument that can be made straight from just the geometry of how the threads are built. All right, but that's, you take the number of threads you have and multiply it by pitch, and that'll give you the lead. Okay, yes?
Where did that tangent lambda equation?
That is not numbered, but it's at the top of the page on page 430. It's right before we get into the section on bolt torque. So the question was, where do you get this equation that I just put on here? The answer is, if you have edition 10, page 430, right before we get into the equation that I put up here. This equation up here is also not numbered, but it is labeled C also on page 430. All right. I don't want to get bogged down here too much, so what I'm just going to say is you can plug in these values. I think this winds up being 0.0529. Okay, we can plug all these values into this equation up here, along with what else? F sub I. What's F sub I? Okay, 28.28 kilonewtons. All right, and when you do all this computing, you end up with, maybe I'll do like my Korean professor used to do when I was in school. I love Dr. Lee. He was great. Anyway, he said, after many dot, and then he would give you the answer. So after many dot, I came out with 52.63 Newton meters. All right, so that answers part C, or at least half of part C. What's my other half of part C? Okay, turn of the nut method. Now this might seem like it's, you might say, well, I know how much the bolt has to elongate, so I just take the pitch, or lead, I should say, and figure out how many turns that is. Yes, sir? F sub C, yeah, so that's a good thing for me to note, is that I gave it in the givens of the problem, and I just basically said anywhere that we've got a friction factor, let's use 0.2, which is, yeah. I mentioned it verbally at the beginning, but anyway, that would either be given information, or there is actually a little bit of information here in the book about this kind of thing, but what they do is they give it to you as what's called a torque factor K for different kinds of bolts. And that actually refers to the equation right after the one that I used here, where it basically encapsulates everything that's kind of friction and bolt geometry oriented into one factor, and you then just use that one factor times the preload times the diameter to get bolt torque. All right, so anyway, that's one of the ways that you can get information like this, but if instead you have friction factors, you can use those like I did. Okay, But the more general answer is that this one here is for threads, and this one here is for the bolt head. So if you know you have different factors there for your friction in the bolt head versus the threads, you can put different ones in right there. Yes?
Do we use like the collar friction table and other stuff that we use for houses, or is that not?
Well, I'll say that the whole idea of being able to find reliable friction factors, I mean, they're hard to find, you know. So what you generally do here is you understand that the calculations that you do are only so good. That's actually probably the main reason why this method of putting a certain amount of preload in the bolt is not real reliable, right? But you go ahead and you sometimes make assumptions and figure out what's at least a reasonable value, and it gets you in a certain ballpark. Okay, so that's, you know, not super satisfactory to people who've been used to dealing in really deterministic terms. But that's how a lot of things work, and a lot of times as an engineer, that's what you're trying to do, is at least get within a range where it will work, and you know, don't worry too much about where specifically you are within that range. All right, so now turn of the nut method, getting back to what I was about to say. Lead relates number of turns to how far the nut has moved. So it would be real tempting here to say, well, I know how much elongation that I need, right? I need 0.051 millimeters of elongation. So all I do is I just figure out what my lead is, and then that's how many times the nut should turn. What would I be forgetting, though, if I did it that way? The bolt is not the only thing that is deforming. Okay? And so not only does the bolt deform, the member also deforms, right? So the total amount of deformation that you need to cause by turning the nut in order to get, you know, the 0.051 millimeters that we want to stretch just the bolt, right? We actually have to take into account both the elongation of the bolt as well as the collapsing of the material that it is clamping, so that we figure out ultimately how to get this amount. Okay, so well, how do we do that? Well, I would say there that the total amount that you have to turn the nut, so this is kind of the second part of part C, I'll call this delta total, is going to be equal to the delta of the bolt plus the delta of the clamped material. Well, how do I get the delta of the clamped material? I need to know the K of the clamped material. Okay? And this actually gives me a great opportunity to show you another equation that when you have certain conditions on your bolted joint, it gives you a much easier equation to use than some of the ones we used last time when we were figuring out the K value for our clamped materials. So look at here. We have uniform material throughout the entire grip, right? That's nice. If you have uniform material throughout the entire grip, you can flip back over to, this is in section 8.5, it's page 421, and they actually boil this down to equation 822. Okay, I'll put that right here, equation 822. And it basically says if you use alpha of 30 degrees, which we pretty much always do, and if you use the diameter of the washer face to be 1.5 times the diameter of the shank, and if you are only clamping just one kind of material, then you can use this expression. And here's what it says, is that it's going to be 0.5774 pi E d over 2 times, the log, not pounds, 2 times the natural log of 5 times 0.5774 L plus 0.5 D over 0.5774 L plus 2.5 D. Okay, so when we plug in our values here, we have the E value of 207 GPa. That's E. D is just 10 millimeters. Down here we have 2 times the natural log of 5 times 0.5774 times the lead. What's the lead? Actually, excuse me. I've been saying lead for L. What's L? Okay. This is one of the things, I'm glad this actually happened, even though it was a mistake on my part. One thing I should say about this book is it does not use consistent letters throughout for different things. It reuses letters. Okay? So it's very easy to be cruising along and see a letter and say, okay, I know what that is, because down here, L was lead. Okay? But, well, excuse me, up here, L was lead. Down here, L was grip. Okay? So what we're dealing with in this equation, L is not lead, L is grip. So what do I put in for that? Okay, 24 millimeters. Okay, and then we have plus 0.5 millimeters, or excuse me, 0.5 times 10 millimeters. And then in the denominator I have 0.5774 times 24 millimeters plus 2.5 times 10 millimeters. All right. So this tells us that K sub B is going to end up at, not B, K sub M. I meant to say M up here. So K sub M for the member, we already found K sub B for the bolt. So K sub M for the member ends up being 2.118 giganewtons per meter. All right. And that means that the amount of delta that we have in the member under our preload is going to be equal to 28.28, which was our preload, 28.28 kilonewtons over 2.118 giganewtons per meter. All right, and what this ends up giving us here is a 0.01335 millimeters, which is definitely less than the amount that the bolt stretched, but it's still not insignificant. It matters. Okay? So how many turns of the nut do we need to do? Well, we basically take this, whoops, I didn't mean to slide that down. We take that amount of deformation in the member, add it to the amount we had in the bolt, and we get a total. I believe we had 0.051 millimeters in the bolt plus 0.01335 millimeters in the member. Okay, so that gives me 0.06435. And then when I put that in to our equation to figure out, okay, this is actually another equation I need to talk about here, is how much theta, how much angle do we turn the nut through? Okay. All right, well, if you kind of think of this as being part of the lead, you basically take how far do you need it to go, which is 0.06435 millimeters, and you divide this by the lead, which is 1.5 millimeters per turn. But a lot of times you're not going to go even a whole turn, and so if you want to convert this into an angle, you can actually set this at, you can multiply by something, and, in this case, like 360 degrees per turn. Okay, and this tells you how many degrees you would need to turn the nut past snug in order to get to the amount of preload that you want. Yeah?
Would the deformation of the member be negative, or would it be like square?
Okay, this is a common question that comes up. The question was, would the deformation of the member be negative? And the answer to that is no, because the direction, even though it is compressing, by compressing, that decreases the amount of elongation of the bolt, right? So in order to overcome that, you need to turn the nut more to get up to the level of elongation that you want, right? So I know that that feels a little counterintuitive a lot of times, but yes, you do add these together because you need to overcome the deformation of both the bolt and the member in order to get the amount of deformation that you want in the bolt. Okay, so now we put in here, let's see, this computes to be 15.44 degrees. Using the turn of the nut method. All right, we're almost there, believe it or not. I know that, we've done a whole lot and we haven't even answered one question yet in terms of a factor of safety or a load factor or any of that stuff. So let's get to that. Part D, the factor of safety against exceeding the proof strength of the bolts. One of the things that we need for that is our joint stiffness constant, because what we're doing here is for the value that they're asking for. Okay, it is, got to find it here, N sub P. And what we see for N sub P is we have S sub P times A sub T over capital C, which is our joint stiffness constant, multiplied by the amount of additional external load that's applied plus the preload. Okay, and so that means that we need C. Keep in mind, C was calculated with K sub B over K sub B plus K sub M. That was back on page 428, equation F. So this joint stiffness constant can be found with that K sub B way down here, 554.6 meganewtons per meter. Over 554.6 meganewtons per meter, plus 2 point, what was that one? Let's see, 2.118 giganewtons per meter. Okay. And punching all of that in, we end up with 0.2075. Okay, what that essentially means is that 20.75% of the additional external load we put on this joint will go into the bolt, and the rest will be relaxed in the member. All right, so N sub P ends up being, what was S sub P? Okay, 650 megapascals. We looked that up out of a table. Here we had 58 square millimeters. Down here we have 0.2075. P, be careful here, we're distributing our 20 kilonewton load across 4 bolts. So each bolt carries what? A quarter of that, which would be 5 kilonewtons. Okay, and to this, we do not do that for the preload, right? For the preload, you take whatever the preload needed to be, and you just add it right on, 28.28 kilonewtons. Okay, and you compute all of this, it ends up giving you 1.286. Okay, and interpreting that value, you basically say it would take 1.286 times the amount of stress in the bolt to get up to proof stress. Okay? Now, because we have this factor that is the preload that basically doesn't change, all right, we often don't want to use this N sub P as much as we might want to use a load factor, which basically tells us how many times additional load can we apply and still be safe. And so that's part E. There's another equation there on page 432. There's equation 829. Okay, this down here, just for note, this was 828. Okay, equation 829 says N sub L is equal to S sub P, which again was 650 MPa, times A sub T, 58 square millimeters, minus your preload, right, which would be 28.28 kilonewtons. All of this divided by your joint stiffness constant times the external load applied to one fastener, which would be 5 kilonewtons. All right? And this basically gives you a number that you can use that basically says you can apply this number of times more load to the joint than what you are. Okay? N sub L turns out to be 9.08. Isn't that interesting that that is so much different than the factor of safety you have against proof strength? Why is this? Yeah, well, probably the best way to say it is that the proof strength number takes into account, you know, all of this preload, and it doesn't sort of take into account that when you apply additional load, not all of that additional load goes into the bolt, right? Whereas the loading factor does take that into account. Okay, so that's what we're dealing with there. So we end up with a 9.08 for our load factor. All right, one more to do, and doesn't take a long time. The last one to do here is the factor of safety against joint separation. Okay, part F right here. That would be equation 830. And equation 830 says that N sub 0 is equal to whatever that preload is, 28.28 kilonewtons, over the additional load, 5 kilonewtons, times 1 minus the joint stiffness constant. Okay, and when we punch those in, this ends up giving us a factor of, a joint separation factor, which would be equal to 7.14. okay? And the fact that that's greater than 1 means that with the load we apply on there, it won't separate. All right. Thank you for your attention. I'll see you guys on Friday.